So thank you very much for the introduction and the invitation to speak here. Ladies and gentlemen, welcome to my presentation about our digital twin of ECOP's rotation heat pump. With this simulation model, we want to develop control concepts for the rotation heat pump. You may know this presentation if you have been to ECOS 2022. Otherwise, just keep listening. For the presentation, I will give a short introduction about the heat pump itself. The rotation heat pump is not that known, and the motivation for the project. And after that, I will talk about the digital twin and simulation results before I end my presentation with a summary and the outlook. So to begin with the introduction. On the left side, you see a conventional compression heat pump, which uses a vapor compression cycle. With the normally known components, we have a cold heat exchanger, the evaporator, then a compressor, bringing the refrigerant to a higher pressure and temperature level, where it is condensed again. Here is the heat sink taking out heat, and then the expansion valve to close the cycle again to come back to the evaporator, where we extract the heat from the heat source. And on the right side, you see the Joule cycle, which is implemented in the rotation heat pump. The rotation heat pump, there is a rotation axis you can see here, and the Joule process needs this, of course, also a compression, which is done by centrifugal forces. So when we are near to the rotation axis, there is a low pressure, and the far away we're going, that higher is the pressure. So the noble gas inside, this is the refrigerant here, has a higher pressure at the outside of the rotor, and also a higher temperature, where we can have the heat sink again, and on the inside there is the heat source. Basic elements are also the heat exchangers, both. The compression pipes, here is a compression pipe instead of a compressor, as we have seen on the normal heat pump cycle. And there is also the expansion pipe on this side. It's not a valve, but it's a pipe. And we need just a fan to keep the refrigerant going around. And there's a special thing about the Joule cycle. We have the working gas always in a gaseous state, so there's no phase change. On the next slide, you see a short film. You can have insights into this. Okay, you get some insights into this rotation heat pump. The media cycles are shown here in detail. The refrigerant, marked by these bubbles here, is a noble gas in a closed cycle within the rotor. And from the right side, we see now the water coming in. It's the heat sink side because it's on the outer heat exchanger at the rotor. And now from the left side coming the source side, the water, which also goes like the sink side through the starter and coming into the rotor also on the sink side. So we need some mechanical sealing between stator and rotor. This is just one challenge to be solved for this system. And the motivation for our project was, there were three challenges. First one was the physical relationships. There is about this rotating heat pump system, there are just little available literature data, and measurements are not easy because there are very high loads on the outer diameter of the rotor. So the transducers and the wiring, they are not able to withstand these high forces. So we had a modeling approach and try to validate these models on a global basis. Second challenge is that the heat pump itself has a robust and flexible operation. There is some sort of problem with the fan characteristics and the system curve because they change with rotor speed and they possibly cause a stop. So the refrigerant cycle is not on anymore because the pressure difference is too low, which the fan can really keep. So the mass flow gets to 0 and then the cycle stops. For this, we have CFD simulations done, and there were just very special CFD simulations to find those combinations to really avoid these forbidden operating points. And the third challenge was to make really controls. For now, we have a presetting of the fan and the rotor speed, which results in a non-optimal control in generally. And with our digital twin, we want to make a controller development in an efficient way. So now to the digital twin itself. It's about the method, then the performance map and the model validations, and in the end, the simulation results and the conclusions. Beginning with the method, as I said before, we had CFD modeling of individual components, which are shown here. The expansion pipe, for example, but more focus was on the heat exchanger of the high pressure side and the low pressure heat exchanger, and also the compression pipe, with also the fan modeled. And this is, of course, dependent of the axis of rotation and the rotation speed. This was done with the ANSYS workbench, and the component showed partly very high deviations from the generally known and validated operating behavior, which is non-rotational operation. So the CFD simulations brought us better understanding of these phenomenological interrelationships of the individual components. The tool we used was OptiSlang. This is an add-on of ANSYS workbench, and it delivered meta models generated directly from the CFD parameter studies. And the parameter studies had automatically chosen parameters for an adequate grid for this meta model then in the end. Having these meta models, we exported them as FMUs and used them in Modelica Daimler, where we just for the beginning tested the FMUs regarding the functionality and plausibility, embedded it then in the Daimler environment. For example, we added connectors, we added ports, concrete values for example, for the rotational speed and so on, and had arithmetic operators for our overall model then. And finally, we combined all these models to build the whole rotation heat pump system to be validated. In green, we see the refrigerant as before, and in blue there are heat sink and heat source, the water connectors. We had some measurement data. Here you see a performance map of 9 steady-state operating points. We have a heating capacity from 300 to 570 kilowatts, so it's quite a range. And we had different outlet temperatures and temperature lifts. When I'm talking about the lift, then it's the temperature difference between source inlet and sink outlet. This was in this project chosen like that. And the speeds of fan and the main rotor, they were fixed. We got with a certain grid through all these points. Not every point was steady enough to put it here in to this performance map. But on the next slide, you can see the table with the exact figures on the left side. So the measurement values and also the speeds of the rotor and the fan, also mass flows and temperatures, inlet temperatures at sink and source sides. On the right side, you have the measured heat on the sink side and the error that we made with our model. Also for the outlet temperature and the lift, as well as for the COP. The axis here in blue, they mark simulations which were not successfully. And in red, you see the largest deviations, so the biggest errors. In the end, we can live with these errors. They are not too high for our purposes. Of course, this depends on what is the aim of the model. For our control concepts to be developed, the tendencies must be right. But of course, we aim to reduce these model errors during the project. So on the axis, you see that we saw that the modeling is quite challenging. So even if you have the separate models of all these parts, it's not easy to bring them into a whole model and then to really have successful simulation results. On the next slide, this is only then simulation results. From here on, we are going just with the model, and we aim to analyze the influence of isolated variables, here the lift, and we try to keep the rest of the variables constant. So on the lower side, you see we have a very small heating capacity of 360 kilowatt, and the sink was always heated up from 135 to 150 degrees Celsius. On the right side, you see now these different lifts. I will go to laser pointing because it's easier. So all these points have had the same lift from about 25 or 29 Kelvin, and the highest lift was then on the right side with about 55 Kelvin. And you see on this axis what to change. We had to change the rotor speed and also the fan speed. And the optimization target in the end with the controls is to have the highest COP. So we see the COP on the left side, on the left diagram, and we can see that in this lowest part left, we have the highest COP from about 3.6, and the lowest COP was on the upper right edge of this operation range. And we see now if we follow, for example, these points having always the same lift and the rest of the variables are constant also, that the COP can rise from about 2.5 to about 3.5. So this is a very large increase. And of course, we want to go always for this point when we know the lift, for example, and given a certain heat capacity, we should set the fan and the rotor speed to this point. But if we go a little bit too far along these points, then the cycle will stop. So this is really, the optimum is exactly on the edge of our operation range. So this is a little bit tricky. And if we go for higher capacities, I will go through the next slides. If you have medium capacity, for example, and then higher capacity, we see that the possible range for speed combinations is smaller then. And also the achievable COP increase. So now we can just increase from 3.5 to, let's say, 3.9 or something like that. So this is also the behavior if we have then, for example, around double the heating capacity from before. But always the same sink temperatures and constant lifts. If we go along constant lifts, then we see this behavior. And another interesting variable is the sink outlet temperature itself. So the utilization temperature of the heat pump. We normally are interested to really valorize waste heat on a low temperature level and put in some electrical energy to go for higher temperatures. Then this is what heat pumps do in general. Here we wanted to find the influence of the outlet temperature with constant heating capacity, constant lift, and constant sink temperature difference. So this the last value is also known as glide on the water side of the sink. And if we go for higher absolute temperatures, while the lift remains constant, then also the COP increases. So if we go, for example, from 105 to 150 degrees Celsius, then you can see it here, the COP rises. Also here, you can see how the color is changing. In this behavior, the rotational heat pump is like a conventional heat pump. This is also connected to the formula of ideal COP, also Carnot COP or some sort of Lorentz COP or whatever you want. This is connected with this formula then. And at last, we can see here the influence of the glide on the sink side, so the temperature difference of inlet and outlet at the sink side on the COP. larger the temperature difference on the sink side, the higher the COP. So the blue are the small glides and the red ones are the higher glides. And the COP is again rising. Of course, with a constant heating capacity and a certain constant lift, and always the same outlet temperature. So these are our tendencies that we found for the rotation heat pump, which were not, let's say, they were not too intuitive. So we did not know about these, and it was not so clear to see such a sharp edge and the form then of the edge. What is a possible and allowed operation range of our two influencing variables, because we just have them two. It's only these rotor and fan speeds that we can really influence. The rest is given sort of boundary conditions or has to be reached in, for example, the outlet temperature. The summary and outlook to end with. We had some steps for modeling on our digital twin. And we have now a successful digital twin of the rotational heat pump. Therefore, we used existing and also externally generated models, also using CFD. They were connected and simulated within Daimler. The model was validated based on real measurement operating points. Of course, there were errors. For us, they were within acceptable limits, but of course, we want to get better. Nevertheless, basic correlations were derived from these simulations. And our next steps in the project are the implementation of different control concepts in comparison in Daimler. And when we have a working concept, especially with this very problem with the edge, the optimum is exactly on the edge of allowed operating range. Then we also implement this on the real industrial scale rotational heat pump, which is at the laboratory of the project partner ECOP. Acknowledgement, of course. Thank you, Klima Energiefonds, and also FFG. And here is what is our project team at the project Rohan. Thank you very much. If you have questions, don't hesitate to ask.
Well, thank you, Bernd, for presenting your digital twin approach for the design of this quite innovative type of heat pump. In terms of the digital twinning of a system in the design phase, like, what would you say are the big lessons learned regarding this simulation plus Daimler approach?
Yeah, there are many. There are many. You mean, I guess this slide. Yeah, there were many lessons learned. For example, yeah, we need the CFD. This is one lesson learned, of course. Otherwise, we don't have enough data for this very special system where it is very hard to really measure. And but inside Daimler, we also had some sort of numerical tricks to be applied. For example, what to really how to really do, because if you go for the fan, this is a very special part. You have sort of characteristic curve, which is dependent on the rotational speed of the rotor of the heat pump. And now we can choose what boundary conditions we give. And if we wish for a certain mass flow coming from the other components, or we go for a certain delta P, so pressure difference, and calculate the mass flow. And this can be done in several different ways, and some are successful, others are not. And on the way, yeah, well, lessons learned is just to try and not to stick too hard on a very certain way. We wanted to do it at the beginning because the other way around may be better. But this is, of course, some experience we also gained in other projects and in other different modeling projects then. But here it was really hard to come to good simulation results, or even to simulation runs which were successful.
So did I get this right? It was about the invertibility of the reduced order model.
I'm not sure.
Okay.
It's invertibility in the end that we knew from the CFD, for example, the characteristic curve delta P and mass flow to be moved by the fan, and we could now give the mass flow and get the delta P out of it, or give the delta P and get mass flow out of it. So very easy to be spoken. But in the background, there are many things to do in Modelica and Daimler to really have it like this. And this was just a different variant of our overall model. And we found it just in the overall model that this could be a problem that does not really be convergent. There was no successful run. And then we tried to really change some variables in parts of this overall model. So in that component models of the own component models. I hope this was clear enough.
Oh, yes. No, I think it really nicely connects back to what Paul and Tom presented in the first presentation. We weren't around then, but they also used some FEM models and coupled them with like another type of simulation to predictions. So, well, I guess we are going to use more of these approaches in the future, and hopefully somebody will come up with a really easy to use and automated approach to just that.
Would be fine. No, this was really much manual work to do, so there were many hours to bring it to this point and to these results we've seen now. There are even newer results. Of course, this is a presentation from ECOS, as I said before. This was in July, and we were busy in the meantime improving ourselves and the project results, but of course the main results can also be presented here, even if the model is not the newest presented today.
Thank you. Super interesting insights.
Welcome.